Alright, we first has to make sure that we understand the insertion and deletion rules of binary search trees. Now, first of all, remember that if we have a data structure that will now be composed of nodes, and each node can have children, and we've decided that each node can have up to 2 children, then we call it a binary tree. Of course, you can have a more generalized structure where a node will have several children, well, more than 2, but we're not going to that right now. Binary trees are used a lot. In real applications, you may find that you may have trees with a lot more children nodes, a lot more child nodes. But for the purpose of courses like these, to make you understand, we normally stick with 2 children. Now, we're asked to insert some values into a BST. The values we want to insert are 20, 5, 28, 45, 34, 67, 92, 10, 53, and 2.
Yeah, that's very interesting.
Let's keep it going.
If we insert 20, of course, we have a tree that just has 1 node in it with the 20, empty left and right children. That's a tree. Most times we don't bother to indicate that there are empty left and right children, but it's good to understand that they are actually there. Normally the empty children are determined by some constant that will describe an empty tree. And there's another example that I'll look at when I finish this that will just make that more clear. So we're then going to insert 5. If you remember the binary search tree insertion rules, the nodes are organized such that everything with a value smaller than the value in the root are placed over to the left. Everything with a value larger than the value in the root are placed over the right. So yeah, 20, 45 goes over to the left.
So if we got that to do in the exam, we'd have to do it step by step like this? Or you just show the end result?
It depends on what you ask for.
No,
I could ask you to show it step by step. If yes, I'd want you to show it step by step.
Okay.
And even if there are quite likely I would explain what I want, but by default, show it step by step.
Okay.
That way you're not confused. I'm going to insert 28, 20. Of course, this board is pretty small, so I'm going to back off my strategy in a little while when I get over there. Then we want to insert 45.
The right of 28.
Right. Then you want to insert 34.
Okay, so left of 28.
Left of 28, it's smaller than 28.
Larger.
Alright, the general rule when you're inserting into a BST is to search for the position that it would go to and then tag it on. So 35 greater than this, less than this. So we'll put our, it's 34 here.
I say that answer is 20, that is greater than 20, greater than 28.
There's a property that the technical name is that the binary search tree has a full ordering property, a fully ordered property, where the position of everything in the tree depends on the value of the node and what's in there before. So to find the position that the 34 would go, we compare it with each node. So first compare 34 to 28. Okay, it's greater than 28. Then we know we need to insert in this part of the tree.
Okay.
Try to insert in this part of the tree. Check to know that the root of that part of the tree, the 34 is greater than 28. Go to this part of the tree. Compare 34 with the value, less. So we know we insert in that part of the tree. There's no empty tree there, so we just tag it on right there. Then we're going to insert 67.
Which will be larger than 45.
So we'll come right here. Then we're going to insert 22.
Which is smaller than 28. So put it to the left.
Then we're going to insert 10.
To the right of 5.
Then we're going to insert 53.
53 to the left of 67.
Then we're going to insert 2.
To the left.
To the left of 5.
Alright, that's the tree. Now the next thing we're asked to do is draw the tree if the values were inserted in ascending order. So the new order of insertion would have been...
Sure. Oh, in order. So you just put them in first and then you do them in order?
No, we're going to imagine that, let's say we first sort the values, and having sorted the values, then we want to insert the values into the tree. Question is what the tree would look like, or what would that tree look like after you've inserted.
Okay.
By the way, given that we have all this data, if we want all this inserted in ascending order, what's the easiest way?
Sorry?
Don't you think the data is already organized here, so that we can get it in ascending order easily?
Yeah.
So it, what do you call it again? So you take up the 20 and create a.
Or does the term in order traversal mean anything to you? Remember pre-order, post-order, in order? Okay. In an in order traversal, you visit the left, visit the root, then visit the right. So if we do an in order traversal on that tree, then remember that a tree consists of a root and a left and right subtree, right? So we're going to do an in order traversal on this tree. And this is just a sidetrack just to get the data in sorted order. So the left part of this tree is that tree. So we're going to do the in order traversal on this tree. The left part of this tree is this node here. So we visit the 2. Root of that tree is 5. Right part of that tree is 10. So we visited the left part of that tree. Now we can visit the root of that tree.
It's 20.
And we'll continue the process. So we have 22,
28.
34, 53, 67. So that's all the values in sorted order. Now, if we wanted to put all of those values into a binary search tree, we know that the first node to be inserted will be the 2. Then we insert the 5, which would be greater, so to the right, and a 10, and a 20. So we end up with one long line of values that really doesn't look much like a tree. It ends up looking like a list. Now, that proves a pretty important point in that one of the advantages of trees over lists is that trees can make our data access times shorter. Whereas if we're constrained to checking each position in the list to determine whether or not we found something, and if there are up to n items in the list, then a search of this list will be a theta n process. Now, because a tree can spread out the data, and we can actually get pretty good performance if the tree is balanced, meaning that, well, if the tree is completely balanced, then you're going to have the height of the tree being pretty much constant from the root all the way down to all the leaves. And there are trees that enforce that, and we're going to be looking at one of those shortly. But the default binary search tree behavior doesn't enforce that. So it is possible to have a binary search tree having a very unbalanced look. And this is really an extreme case. It's what you call a pathological case, where the tree just behaves badly. If it behaves well, we want to get something like a login performance for the search. Because if you have n nodes in the tree, the number of times that you'd have to search from the root down to the leaves will be proportional to the height of the tree. And if the tree is balanced, then the height of the tree is log to the base 2 of n. That was proven previously. We don't have time to prove that right now.
Okay.
Now, if the tree is not balanced, we can degrade to a theta n performance. Oh, we're supposed to delete value 20. Now, this tree here, when you're deleting a node, there are two things that we do. You first do a structural, or you do a logical deletion, then do a structural deletion. The logical deletion involves copying a value from somewhere in the tree to the node that you're going to remove. Stick up in there are 3 cases. In the first case, the node that you want to delete has no children. For example, the 5th tree. In that case, you can just get rid of it. In the second case, the node that you want to delete has 1 child. So in that case, what you do is slide up the child to replace the value. So if you want to delete the 67, you just slide up the 53 to replace that. So in short, you would then just make the link here, just point to this node. In the third case, the node you want to delete has 2 children. So in that case, you replace the value of the node that you want to delete with another value. That would be a leaf node. And then you structurally delete that node by just getting rid of it. Now, the process of replacing the value involves finding the next value in line to this. Now, in this course, what we'll be using is the next value up. There are some books that use the next value down, but we're using the next value up, which you call in-order successor. So in this case, the next value up would be 22. You can easily write a program to find it by checking the leftmost node of the right subtree. So the first thing we're going to do is copy 22 up there. So we're going to have the 22 as a root, then 5, then 2, then 10. Then the 28 now will still be to the right of 22. This node here that formerly held the 22 is going to now be structurally deleted, so we can just get rid of that one. The 45. The rest of the tree just tags along right here.